help with that. Halogen electrophiles, we're going to see those again today. So things like chlorine, bromine, iodine. We actually saw these in the very beginning of our class when we were talking about electrophilic aromatic substitution, right? We activated these with, it should be BR2. We activated these with our Lewis acids, and in this case we have a stronger nucleophile, so we'll use these just as electrophiles. And you've been talking a lot about keto-enol tautomerization, which technically you did learn the mechanism of in 2301, but certainly we've revisited in 2302. So feel free to go ahead and take a look at those topics. As a reminder, these resources of what you should review before the lecture is all posted on Canvas. So if you want to review these things ahead of time, you can go ahead and do that. All right. There's a typo. Objectives. Learning objectives for today are we're going to talk about some enol chemistry as well as a new kind of mechanism. It's similar to some mechanisms we've seen before, but something called a conjugate or 1,4 addition to an alpha beta unsaturated carbonyl compound, like a ketone or an aldehyde. And we will do some of that with enolate chemistry, but we will also do some of it with some copper chemistry as well. So we'll introduce a new metal, copper being element number 29 on the periodic table. All right, let's go ahead and get into this. Our first learning objective is learning objective 21K. We're already into chapter 21. This is the last day of chapter 21, then we'll move into chapter 22 about amines next on Wednesday. All right, so this is a 4P, so we'll learn about the mechanism of this. And this is for the formation of alkyl halides. Right, we use alkyl halides all the time. Here's one way to make them. And this is going to be from halogenation of ketones. All right, or aldehydes if we have the correct type. You'll see what I mean. And if you're following along in the book, this is 21.6. Okay, so thus far, we sort of have taken a look at this tautomerization mechanism that we've seen in 2301 and now revisited in 2302. So we start out with something at the alpha position, right? We've labeled this alpha CH bond. And we've seen this equilibrium where most of the time it does exist in its ketone form, but this equilibrium does lie partially to the enol side of things, right? So actually, if you were to take an NMR, if you all remember NMR spectroscopy from 2301, if you were to take an NMR of this compound, you would see a bunch of signals for our ketone form, but you would also see this enol in solution as well. And how much of that you would see depends on the electronics of our compound. Sometimes it's like so little, it's like 0.1%, you might not observe it, but sometimes the enol form will actually end up as maybe 10 or 20% in your reaction mixture. All right, so when we're thinking about this, let's think about where our delta minuses are. We know our delta minus is that those lone pairs of electrons in our oxygen. We've learned that this alpha position, because we have this enol form here, is another delta minus. And then, of course, throughout this entire semester, we've seen a lot of reactions at that carbonyl carbon, which means that's our delta plus in this reaction. All right, so for this particular reaction, we're going to use the enol form as our nucleophile. All right. Okay, so how we're going to start this out, but what we're going to draw is we're going to draw our ketone as our nucleophile, and we're going to draw it in the form that exists most of the time, right? So we double check that this has an alpha hydrogen. Of course, it has 3 alpha hydrogens. We don't need all of them, so I'm just going to draw one in, and this is our nucleophile. And then we're going to have our electrophile. So X2, where X equals chloride, bromide, iodide. Just like normal in our periodic trends, we don't see fluoride as an electrophile here. We don't see F2 being used because it's just not reactive enough as an electrophile. All right, so we're going to do this in a little bit of water to help us with our proton transfers. And our product is an alkyl halide that replaces that CH bond. All right, so we have our X at this position. And then our byproduct of this reaction is, of course, H, because we've lost that alpha hydrogen, and then our other half of our electrophile, where that's that X. So something kind of fun in chemistry happens where sometimes the first time you make something, it's a little bit slow, but then you produce a byproduct, and actually this acid helps the tautomerization. So this reaction actually goes faster the longer you run it, right? It's not like a linear conversion here, because we know that acid helps to catalyze tautomerization, right? So that's kind of it's like an autocatalytic reaction, but it's kind of a fun little fact. We see this quite often in chemistry. All right, so let's just write down for ourselves that we can use chlorine, bromine, iodine, and not S2. All right, that's just too electronegative, right? We know that's the most electronegative atom, and so having it act as the electrophile, it just doesn't work out very well. All right, but the product that we form is an electrophile, an alkyl halide, right? So we've seen so many reactions that use alkyl halide as an electrophile. All right. So kind of cool what we've done is we've taken this, which would be the normal, this functional group, this ketone. This would be the normally electrophilic position. And now we sort of change that electrophilic position to the alpha position for that X. We've also taken this carbon here, which was part of our enol, and we've turned that from a nucleophile into an electrophile. All right, so these are functional group manipulations so that we can kind of get where we want. Okay, now let's talk a little bit about the mechanism of this reaction. All right, so we've already talked about the mechanism of tautomerization. And so you all know that already. So let's start out with the enol form or mechanism. All right, so let's do this reaction with bromine, for example. All right. So in this case, we know that our oxygen of our enol can help kick off our mechanism. So that lone pair on oxygen can come and make a double bond between our carbon and oxygen, which causes this double bond of our enol to really want to be a nucleophile and break apart. We're going to attack one of our bromines. And then we can break that bromine-bromine bond and return those electrons to the second bromine, turning it into a bromide. All right, so what we see here is we have a double bond between our oxygen, but it still is protonated, which means we need to give it a positive charge. We now have a single bond where our ene of our enol was, and it is now bound to a bromine. Right, the bromine still keeps its 3 lone pairs of electrons, and now it has 1 bond to it, so it's a neutral species. And you'll recall that we broke that bromine-bromine bond so that we gave those electrons to our second bromine, turning it into bromide. And now we see this nicely balanced reaction. All right, so now we can go ahead and form our acid here, where we take the lone pair of electrons on the bromide, and we have it deprotonate, so attack that hydrogen-oxygen bond, which causes that HO bond to break and return those electrons as a lone pair onto our ketone. And that is how we get to our product, right? We've neutralized it. We have one new bond here with our bromine. Our second equivalent of bromine is now part of HBr. If you wanted to draw that as H3O plus because this is in water, that would be totally fine. So the water is necessary just sort of as a proton shuttle. It can help that deprotonation if the bromide is in such lower concentrations. So that would be very accurate as well. Okay, so alpha halogenation only happens once under acidic conditions. So we didn't add acid to this, we formed acid, all right? So now let's take a look at our product here and see what I mean by the possibility that, oh, maybe this could react a second time. Okay, so this is our compound here. But of course, we know that this could have a tautomer as well, right? So if this tautomerized, that would give us an enol back. And now instead of two protons on the end of that enol, we'd have our bromide, right? But we know that halogens, like bromide, are electron withdrawing. So this is not nucleophilic enough to react again. There are conditions, which we don't need to know for this class, in which if you were to add a base to this, you could create an enolate, which is, of course, a better nucleophile than an enol, and we could do this reaction. But for the purposes of this class, we're going to stick to the fact that this particular intermediate is just not nucleophilic enough. All right, so if any of you thought, hey, that looks like something that could react again, you're absolutely on the right track there. But for the reason that that bromide is there, that electron withdrawing group, we don't see that again. All right, so let's take a look at our first chime-in question for today and make sure that we are kind of getting this concept. So our first question for today, we have pretty different concepts, so there's two questions today. Talks about understanding what is the product of this reaction. All right, so this is with iodine. We have to sort of recognize where the alpha position is, recognize the role of the water. So we'll see what everyone thinks of this. All right, it's looking like most people have answers. So let's see. All right, so overwhelmingly, we do have B as a response. So I really like that. That's the correct answer. I definitely understand why D was the next runner-up, right? Because sometimes it's hard to think about what is the alpha position in this situation. And so I definitely understand why people chose D. So I'll give you a tip for helping to figure out sort of to distinguish between B and D. Of course, we have a couple of different answers, A and C. We have seen water form acetals and things like that. So again, I definitely understand why people are getting some of the other answers, but it's nice to see that the majority of you all are kind of on the right track with thinking about that alpha halogenation. All right, I don't see anyone else responding. Oh, there's another one. Good people. Again, you don't have to get the answer right. You just need to respond. So I think sometimes people change their answer, which is totally fine, but you don't need to. All right. Okay, so let's go ahead and take a look at this and kind of give ourselves a tip for how we figure this out. All right. So we say that we draw carbon skeletons out without their protons and things like that for ease of understanding the molecule, right? Because if we were to draw this hydrogen, this hydrogen in, this hydrogen in, this, right, we start to get a really complicated looking molecule, right? And it's hard to see where things react. So that's why we draw out the carbon skeleton. But actually, I would say that's sometimes a bad thing that we don't draw everything out. So in this case, because we know our learning objective has to do with α-halogenation, if I was you and I saw those reaction conditions, I would draw out those CH bonds. And I think that will be a nice tip for you to understand where we should think about reacting here. So this is the alpha position. This is, of course, beta. These are both gamma. So we're going with that alpha position. All right, so our CHEM had iodine 2 and H2O for this reaction. And the product of the reaction is going to be halogenation at the alpha position. So we can see that we have our alpha position here. We discussed the reason why we only iodinate once, right? Because that enol that we formed up here with a halogen on it, even though we can see a tautomerization there, we know that's not nucleophilic enough. So that's why we've only gone once, right? So, we can always think about the alpha halogenation, making sure that makes sense to us. And then let's think about the enol isomer that actually serves as our nucleophile. So this is going to be what's actually serving as our nucleophile. We see that there's just a single H there. All right, so this will be our nucleophilic carbon. So there's a couple tips that you can help yourself with by drawing in those CHs and those alpha labeling and things like that. All right, so we're going to change what's going to seem like changing gears quite a bit here on our learning objectives, but enols are going to be soft nucleophiles, so it'll kind of come together in the end, all right? So this is going to be learning objective 21L, and this is going to be to identify. So whenever we have an identify learning objective, there's probably going to be a bunch of options, and we need to figure out which of those matches. So identify if a nucleophile is hard or soft. All right, we've talked about hard, soft, acid, base theory previously, and so this kind of comes into play with nucleophiles as well. So this is 21.9 in your book. Okay, so let's recall what hard, soft, acid, base theory is. All right, so we said that, one of the things we need to think about in hard, soft, acid, base theory is localization of where is the charge localized. And so it turns out that nucleophiles are very much just bases, right? Where your electrophile is a proton. All right. So sometimes you think, oh, those are probably really different things. But actually a nucleophile is just a base. All right. So we can say that a hard nucleophile, we've seen some examples that I'll give you, is where the charge is very localized on the nucleophile or the nucleophilic position. It's going to go on 2 lines. All right, so some examples that would be good is something like N-butyl lithium. All right, so here we've drawn N-butyl lithium as the equivalent to that carbon being an anion and lithium being a cation. Right, there's nowhere to delocalize. There's no resonance on that butyl, right? It's just stuck there, right? So we consider organometallics like N-butyl lithium, as well as I could draw for you this benzyl magnesium bromide as very hard. Excuse me. All right. So organometallics that we've learned thus far are going to be hard nucleophiles. And I'll teach you today how we can make an organometallic into a soft nucleophile. So what is a soft nucleophile? Well, just like in hard, soft, acid-base theory, we're thinking about delocalization of that charge and polarizability. So this is where the charge is delocalized. So an example of this would be resonance or something that is polarizable. Right, so polarizability is the ability to sort of polarize where an atom cloud is in a nucleophile, all right? So for example, something like, even though we're gonna see that this thiolate, this is negatively charged, not positively charged. This thiolate is negatively charged because sulfur, when we take a look at the periodic trends, we look at sulfur as element number 16. It's below oxygen. That means it has more, its nucleus is much different than that of an oxygen, where all the protons and neutrons are, so that it's a much more polarizable molecule than, for example, if we had the alkoxide of this, the oxygen version, all right? So enols are nice, soft nucleophiles, right? When we take a look at our enol form before, we see here that there's a lot of delocalization of that nucleophilic position, right? It's all over the place because we have resonance, all right? And then the other one that I'm going to teach you about today is organocopper reagents. All right. Okay, so let's compare and contrast to organolithium reagents. I've shown you this organolithium reagent as a really hard reagent. We have nowhere to delocalize that negative charge. Let's take a look at where lithium is. Ooh, element number 3, that's super cationic. It's really not going to be great for that. But let's look at copper, element number 29 in the periodic table. We now are in the D block. So we have a lot of D electrons that we can play around with. And so this leads to a lot of polarizability of where the negative charge is. So I'll draw those reagents out for you. Okay, so now that we can kind of understand and differentiate and identify a hard and soft nucleophile, let's see where the reactivity is different, right? Why do we care about hard or soft nucleophiles? Well, we want to see how they react differently, all right? So that's our next learning objective. So this is learning objective 21M. This is going to be a 4P. So we're going to learn a mechanism of this. This could be a little bit different for us. So the 4Ps for, sometimes this reaction is called conjugate addition, or sometimes we call it 1,4 addition. All right, and I'll show you what that 1,4 means. So this is the 4Ps for conjugate addition reactions from alpha, beta, unsaturated, meaning there's a double bond there. It's unsaturated, not fully saturated. So alpha, beta, unsaturated carbonyl compounds. And soft nucleophiles. We can, of course, react hard nucleophiles with these compounds, but you don't get 1,4 addition, all right? And this is in chapter 21.9. All right, so before we sort of see where these react and compare with our hard and soft nucleophiles, let's get straight what this actual functional group we're talking about, this alpha, beta, unsaturated carbonyl compounds, all right? So let's go ahead and take a look at this. Okay, so we know that we can have our numbering system on whatever type of ketone that we like, all right? So we've already established earlier today that we call this the alpha and beta position. We've actually established that a long time ago. So when we take a look at this, we can say this is an alpha beta unsaturated, meaning it has a double bond in it, carbonyl compound. Okay, so that checks out for what we're thinking about this compound. Now let's understand what this 1,4 addition situation is about. So we also learned when we first learned about ketones that we could label the oxygen the 1 position, the carbonyl carbon the 2 position, the alpha position is the 3 position, and the beta position is the 4 position. Right? We had 2 numbering systems when I first taught you this, and I said it can be a little bit confusing, but that's okay because they're meaningful in their own ways, all right? So we have 1,4 addition, meaning we're going to add bonds across the 1 and 4 atoms. Okay, so now let's see what where our delta plus and delta minus is going to reside in a compound like this. All right. So let's draw our resonance structure. All right, this is not equilibrium. This is an extreme resonance structure. Right, so previously we're pretty comfortable with the fact that this is delta plus and we have delta minus here. We don't see any alpha hydrogens that are going to come off in this reaction. So instead, we're going to think about this resonance structure, that what if we moved this double bond to form a double bond between the carbon and the base of the carbonyl, and then we were to break that CO double bond and put those electrons on our oxygen. So you'll recognize this kind of looks like an enolate. All right. But because we've broken a CO double or CC double bond in our alkene, that means we have a positive charge at that 4 position or that beta position, right? So this is a pretty extreme resonance structure, but that will help us to understand that at the end of the day, when we're thinking about the 2 electrophilic positions here on this molecule, we know that our delta plus is on our carbonyl, which we know quite well, right? We've seen this before, that electronegative oxygen. And because of that ability to have that resonance structure, we also see that the 4 position or the beta position is also electrophilic. All right. So this is how we can think about this as a electrophile. So both 2 and 4 positions are electrophilic. All right. So our enol chemistry, we're taking a look at the oxygen and the 3 position being nucleophilic. And now we see that, so that was the 1 and 3 are nucleophilic and the 2 and 4 are electrophilic. Okay, so now let's take this and let's understand what happens when we react with our various types of nucleophiles. So if we were to add in a hard nucleophile, right, something negatively charged, what we would see is it does not touch our double bond, but instead it does the type of reactivity that we've seen before where it adds to the base of the carbonyl. All right, so 1,2 addition, this is called, because we have the 1,2 positions on our carbonyl carbon. So 1,2 addition, we've seen this before, happens with not hard nucleophiles. Right, this has to do with the orbital overlap, which is a little bit beyond this class, but if you take a next chemistry class in the sequence, they would definitely talk about sort of the reasons why. So I'll tell you it has to do with the molecular orbital overlap. Okay, so now that we've established for a hard nucleophile, what about these soft nucleophiles that we're just talking about today? All right, so we have the 1, 2, 3, 4 position. So if we take in a soft nucleophile, as our learning objective tells us, it's going to do a 1,4 addition. So the product of this reaction will end up being the oxygen will still be negatively charged. We sort of use resonance this whole time. But we have our nucleophile that adds to that 4 position. All right? So 1,4 addition. Sometimes, as I said, this is called conjugate addition. Happens with soft nucleophiles. This has to do sort of with the orbital overlap of a better carbon-based electrophile versus the one that's right at the base of the carbonyl. All right, so we can add a nucleophile to the same functional group and get different outcomes, which means it's very important for us to sort of assess, are we using a hard or a soft nucleophile in the reaction, right? So that was why our learning objective before was to figure out what we're actually using in this reaction. All right? So same electrophile, different outcomes. All right, question. Yeah. Yeah, that's a great question. So we will walk through the mechanism in just a moment, and I'm going to get to that exact question. Does that sound good? Yeah, so that's just where it ends up, but we will talk about the mechanism, the P4, and it will, it's a great precedent to that question. Okay, so now let's do one example that we know of a hard nucleophile. So a great hard nucleophile would be something like a Grignard reagent. All right, so something like a methyl magnesium bromide. All right. So we would go ahead and we would have our electron density from our methyl magnesium bond would go ahead and add in at the 2 position. And then that would break that CO double bond and place our electrons back onto our oxygen. All right. So we haven't done anything to that double bond, that CC double bond. Nothing has happened there. What we've done is we've made an alkoxide, so negatively charged. We've added in our methyl group, and then our magnesium bromide is going to be our counterion. All right, so we know with these types of reactions that we need to do something like an H3O plus workup, right? Water or a bit of weak acid. And then we know that we protonate that alkoxide to form an alcohol, right? That's the only thing that this H3O plus workup does, right? We've already made our carbon-carbon bond, but we get to this as our product. Okay, so this is, we've seen this before. We've seen 1,2 addition. We didn't call it that. We just called it addition to a carbonyl. Now let's go ahead and see what happens with the soft nucleophile. We'll be able to answer your question. Okay, so we'll take our exact same electrophile, but instead we're going to use in this case, we will use a thiol. So, right, recall our sulfur was a pretty soft nucleophile, very polarizable. We could use the thiolate, that's fine too. All right. So now let's go ahead and see. We have 1, 2, 3, 4. We know that this is going to be P4 for conjugate addition. So drawing all of our lone pairs. All right. So what we're going to see is the lone pair on that sulfur is going to attack at this 4 position. That's going to form a C sulfur bond there, which means we have to break our CC double bond. We're going to place that CC double bond. We're just going to move it around that ring. And that means we have to break our CO double bond as well and place those electrons on our oxygen. So this is a sort of cascade reaction that has to happen because of the number of bonds that we can have to carbon. So we have to accommodate that by sort of keeping going in this reaction. All right, so this is what we're going to end up with. Our sulfur has our hydrogen still bound and our phenyl group. It's positively charged because it was a neutral species that attacked. All right. So now we can go ahead and think about a proton transfer here. So in this case, we can have our oxygen lone pair reform a CO double bond and use our enolate to deprotonate this sulfur. All right. On that intermolecularly or intramolecularly, it doesn't really matter to me with proton transfers. Okay, so now let's see here what, right? Because we don't want this enolate. We want something that's a neutral species. So we have reformed our CO double bond. We now have our hydrogen. And we have, should be a blue hydrogen here. And now we have our thiolate. Sorry, a thiol. All right, so this is a nice way to think about the different reactivity of different types of nucleophiles. So at the end of the day, what we see here when we formed this sort of double bond in this enolate position, it's due to this cascade of arrows. We have to add to that unsaturated carbon, then we need to break that double bond and reform it because we can't have 5 bonds to this carbon here, and then we need to go ahead and protonate this. All right, so that's P4 for this mechanism. Does that answer the question? Okay, awesome. Okay, so another form, I did this with sulfur. We can do this with enols and enolates, and I'll show you an example of that. But let's go ahead and take a look at some organometallics that can go ahead and do conjugate addition for us. All right, even though we said up to this point, the organometallics that we know, like these lithium reagents and magnesium reagents, are really hard nucleophiles, so we have to use them for 1,2 addition. Our organo copper reagents can come to the rescue. So sometimes we call this cuprates, right? So cuprates is from the old-timey word for copper too. These are going to be soft nucleophiles. All right, so we can take our alpha beta unsaturated ketone. We can add in for our reagents, these copper reagents. It's gonna be a little bit confusing because they also have a lithium counterion with them, all right? And then, so that's gonna be step 1. Then step 2 is gonna be H3O plus workup. And the products that we get out are that 1,4 addition. Or R group in this position. So R can be an alkyl, it can be an aryl, it can be an alkynyl, it can be really sort of any carbon-based group. Okay, so these have a lithium in it, and it's a metal copper bond. So why can these be soft nucleophiles? Let's see here. All right, the reason is that copper is going to have our methyl groups bound to it. And sorry, it's a copper 1 reagent, not copper 2. So it's a copper reagent, it has a negative charge on it, and our lithium is the counterion. All right. So let's contrast that to our hard nucleophiles, right? Or methyl lithium. Let's do that. It's the closest one. And we said that that is equivalent to our methyl group having a minus charge and a lone pair on it and a lithium plus. Now what we see here is our nucleophile is this metal carbon bond, but the negative charge resides on this really electron-rich copper, element number 29. So we don't need to worry about that negative charge being on the methyl group, so it's a very soft nucleophile. All right, so let's see if we sort of understand that concept, and let's go ahead and do our second chime in for the day. All right, so thinking about how could we make this particular molecule? What would we need? What could get us to the end? I have a couple methyl sources, 4 different methyl sources. So you can kind of think about, okay, those are our source of methyl, but what about this alpha beta unsaturated ketone that we have? And think about that 1,4 position versus 1,2. All right, let's see what people are thinking. All right, great. So a lot of people have very correctly identified B is the correct reagent, all right? So it's a very soft nucleophile. A and C are both hard nucleophiles, and so they would go to the 1,2 position at the base of the carbonyl carbon. And then I like that people were not tricked by methyl iodide. Methyl iodide is not a nucleophile, it's an electrophile, right? So it's an electrophilic source of methyl. All right, awesome. I'll go ahead and draw out the answer for you on the next slide. I think that's how many people we had respond before, so I'll close this. All right, great. So our chime in was sample here. We have an alpha beta unsaturated ketone. We already have a methyl group bound to it, but we want to get a geminal dimethyl group, or a gem dimethyl. So we first added a reagent, and then we had our workup conditions. All right, so let's go ahead and see here. Well, our soft nucleophile that was the winner was our copper reagent, right? Our cuprate. So dimethyl copper. We have our lithium counterion that we saw up here. All right. Our hard nucleophiles candidates were organolithium reagents, methyl lithium, as well as methyl magnesium bromide. And these would add 1,2, not 1,4. And our methyl lithium, that was sort of our red herring, was actually an electrophile. So an electrophilic source of methyl. Methyl iodide. All right. So we need to just think about this. 1, 2, 3, 4, right? What type of nucleophile, once we see there are 2 possible sites of addition, then we need to really identify our soft nucleophile. All right, our final example for today will be an example of an enolate, or an enol as a soft nucleophile. All right, so these are soft nucleophiles because we have a lot of delocalization. All right, enolates, a soft nucleophile. Sometimes we call this Michael addition. I don't know who Michael was, so I like to call it still conjugate addition of an enol. But you might see that in your book, a Michael reaction or Michael addition. Okay, let's start out with a potential enolates here. All right, say we have a methyl group here and a hydrogen. All right, and our coupling partner, as you might have guessed, is an alpha beta unsaturated carbonyl compound. So you have 1,2 addition as an option, or 1,4 addition as an option. Okay, let's add a little bit of base to this reaction. a little bit of water. All right, I'm going to have you all write the product of the base. So what is the product after you deprotonate this? So we have a couple of different hydrogens that we could deprotonate. We actually have 5 viable choices. So think about which of those are going to deprotonate to form our enolate nucleophile. All right, so just identify which proton. So when we're considering, I had this question in office hours, how do we know which proton? Let's identify the fact that this is one electron withdrawing group, and here's a second electron withdrawing group. Now, this proton here has 2 electron withdrawing groups near it. All right, these protons have 1 electron withdrawing group near them, right? So we would go with the most acidic proton, which is the one with 2 electron withdrawing groups, all right? So that means our enolate would be, look like this. Now we could have, drawn the enolate with the other ketone as well. That would be perfectly fine. Okay, so now we have this enolate. Now we needed to add 1,4, all right? So after we work this reaction up, let's get our skeleton of our carbon here. All right, we have the 1, 2, 3, 4 position, and that's where our enolate carbon is going to be bound, all right? So we have our methyl group, and then we have our ketones, all right? So this is the bond that we have made. It's 1,4 addition. And here is our nucleophilic site here. All right. So the mechanism of that reaction, I won't draw the quenching of it, but the mechanism of that reaction would have our lone pair of electrons from an enolate come down, reform our CO bond. It would then have our double bond come and add into that 1,4 position. That would break that CC double bond to form a CC double bond between the 2 and 3 positions, which would break our CO bond and give those electrons back to our oxygen. All right. So that 1,4 sequence is going to be the same always. Just think about where your nucleophile is.